So really quick show of hands. Okay, this is the audience participation portion of the day. I'm going to be down here because I can't stand behind a podium for very long. I go crazy. So how many people, is this your first SDC? Wow. Welcome. Welcome. Thank you for joining us. This is fantastic. And how many people here have heard of something called AI? All right. And how many people have already started the AI drinking game? Most people are still suffering from that from last night. What I wanted to do and talk about today is I wanted to give people an understanding and a description of what it is that we have been doing here inside of SNIA. You heard James talk about the OCP relationship with SNIA, and I'm going to talk a little bit about that as well a little bit later on. But ultimately what we're trying to figure out here is how do we solve a very real problem. Now, one of the problems that we have is that everybody wants to put AI in everything, right? And you find yourself with an AI wash. What do? You take, I think Addison had a really good point earlier, is that HPC, you're doing weather calculations, is now called AI, right? So how do you distinguish between those kinds of problems and the real problems? Well, one of the real problems is that when you start to look at how much data you need, like from a data, when you look, sorry,
not if you're going to pose.
Not if you're going to pose. When you start to look at the data problems, right? When you look at it from a data perspective, and we all tend to look at things from our own individual points of view. I happen to work for a company that works on processors, so for the people that I speak with on a regular basis, they think of it from a processor perspective. I also happen to work with a lot of networking people, so the networking people all work at it from their perspective. We do storage, so we think of it from a storage perspective. And of course, everybody's doing the real important job. All anybody else has to do is what we tell them. So when we start to look at the data situation for AI workloads, like real honest to God, not the AI washing part, but the actual problems with data. The issue is that the data that you need is not the data that you get. So you have to turn the data that you get into the data that you need. When you do that, you create more data. Not just a little bit of data, a lot of data. That vector matrix mathematics can have additional amplification from the original data, not 2 times, not 5 times, not 50 times, but 100 to 1,000 times more data to process the data. It becomes a data tractor pull, right? So that's the problem. That's one problem. That's not the only problem. Because the issue is that when you have that data, you have to put it somewhere. You have to move it somewhere. You have to put it somewhere when you move it. And that is where we're trying to figure out how to do this, because everybody's got an idea about what to do it at a specific point in time in the equation. Now, for those of you who went to Curtis Ballard's AI for Storage 102 session, you may see something very similar. It just happened it was a coincidental aspect that when people think of a simplified approach to doing AI, and this is just training, this is not inference, they break it down into some very useful blocks. Right? You've got to take the data in, you've got to ingest it. Then you have to prepare the data. You have to train the data to be trained. Then you have to go through forward and backwards passes. You have to be able to move it between different GPUs and so on. And along the way, you'll notice, for example, there's a very, very, very important part that's missing here. It's called checkpointing. Now, when you start, I see nodding heads there. Yes, this is not a trivial problem. This is sort of like the assume a perfect scenario situation. You ever remember in high school, every physics class had the same guidance to the students? Assume a frictionless environment. Now, the way that people see this is this way. The way that people think about this is this way. Right? Now, in reality, this is actually what winds up happening. Every single time you do an AI epoch, it is multiple workloads all strung together. And as you probably heard several times in a number of different presentations, each and every one of these types of workloads has a unique data requirement. So we touch everything. We touch tape. We touch disk. We touch memory. We touch HBM. We touch at some point in time this happens. And if you only look at it from a processor perspective, or if you only look at it from a network perspective, you will zero in on a very narrow element of the problem. Because if you may be talking about large sequential reads, or you're talking about a lot of small files, Addison had a really good point about the small file problem, right? All of those different things, well, that's not my problem. Garbage, right? It is your problem because eventually, if you're sitting there with a $10,000 GPU and 40,000 of those, if that GPU isn't doing work, if you're waiting for the data to come to your GPU, you have a problem because you have a lot of power going into these different systems. GPUs are not cheap to run, and they're not, especially not cheap to be idle, right? So as we start to go through this, we have to see the roles of each of these different places, where the data has to be and what kind of data it has to be where it needs to be, is unique in the sense of where it is at a particular point in time. Now the issue here is that there is no standardized way of getting data from a specific place to another specific place. That's fine. This is a big problem. There's a lot of different moving parts here. So what we want to do is we want to make sure that we take the data and we get it into the GPUs in the proper way. How do we do that right now? Well, inefficiently, right? So what you're seeing here on the screen is a graphic that involves a node, right? A node in this particular case has a couple of CPUs, it has about a few GPUs, and it's got different types of networks. It's got a scale-up network between the GPUs, it's got a scale-out network between the nodes, and then you've got a front-end network. Right? That front-end network is typically where you see your data now. There is no indigenous standardized way to get data into your accelerators. None. Doesn't exist. Doesn't happen. So what do we have to do? We have to go all the way around Robin Hood's barn to get the data from the front-end network through the memory buffers of a DPU or an RNIC or a NIC or something like that into the kernel of a CPU, into the memory buffer for the GPUs, get the memory GPUs to talk to one another so that they can actually have these, the parallelism necessary to run the program in the first place. And that's assuming it's in the right data structure to begin with, right? I'm not even talking about half of the other things that goes along in the process. So when you start to add up all these different things at different stages along the way, we've got a horizontal problem over time, and we got a vertical problem. We got a vertical problem of all the different touch points that have to happen. And where these things become something of an issue is that there's no real guaranteed way that everybody's going to do it the same way. That's what we're trying to solve. That's the problem. That's not AI washing. That's a real problem. So when I talk about networking, for example, when I do presentations for UEC, I talk about a concept called good put. Anybody not know what good put is? Everybody knows what good put is? Cool. Because what's that? So the ratio of actual work to final work is what we call good put. How many things do we have to do in order to make the things go work? You want that ratio to be really, really favorable. Meaning, I don't want to have extra stuff. I don't want to have a lot of headroom. I want to make sure that I get the most efficient way possible. What is the most efficient way possible for a GPU to do work? To have direct access to that data. But when you start to piece together all the things that you need to do, we're not just talking about the access to the data. We're talking about initiation of the data, security of the data, management of the data. All of a sudden, you start talking about what SNIA does. Right? We do transport, we do security, we do memory, we do compute near to the data storage, and so on and so forth. But the issue here is that getting the data into the network itself is non-trivial. Right? So for instance, and this is true individually inside of an individual processor, by the way, not just even across companies. Right? So if I have a processor type, I have an accelerator type, and I do checkpoint, and all of a sudden I want to get a brand new super duper processor plus 10, I can't use that same data. Why? Because the data is vectorized for that particular processor. So that means that all the work that I've already done has to be completed either with the original processors because I can't migrate it. There's no migration path. Not in any way that you can guarantee. Right? So you have to go all around Robin Hood's barn, or if you're familiar with the family circus, which is what I grew up on, you see Billy going around all of the neighborhood to get all the different places to get the data for the GPUs. Right? So when we want to get the data into the correct form, into the correct processor at the correct time, and leave the least amount of idleness inside of the GPUs, reducing our power, reducing our cooling, and so on and so forth, we need to have a good way of thinking about this from a holistic perspective. And that's what Storage.AI is. It is a holistic solution. Now, what does a holistic solution look like? Well, If you want to go and do an AI version of ChatGPT to figure out what Storage.AI is, which is really interesting, by the way. We announced Storage.AI in July, and by August, ChatGPT and Gemini already had an answer for it, which is scary, I guess, if you think about it. But ultimately, what I'm trying to point out here is that we can make the whole workloads work together better across the epoch, across the different types that need to be done, and we can do it by making the data work more efficiently. And we can do this by not just with the work done inside of SNIA, but as James was pointing out, the work that we can work with OCP, the stuff that we can do with UEC, the stuff that we can do with DMTF, and so on and so on and so on. Why? Because the problem is that big. It is that huge. There is a lot of work that needs to be done. Right? And that work that needs to be done has to be done in a holistic perspective. We want to reduce the data amplification, the I/O amplification. We want to make sure that this is secure. For instance, right? Think about this for a second. From a needs perspective of the processor, it's not so simple as saying, I'm going to put an OS on a GPU. There's far more stuff that we actually have taken for granted in the way that we currently do storage, right? File, object, block. All of these different things we would have only one if there was only a need for one. But now we're talking about, hey, I want to do not just block, not just file systems for AI, but I also want to use direct access with object. As a matter of fact, I did this presentation before the BOF last night. The conversation about doing object using RDMA or Ultra Ethernet got so excited, they actually started having talks about a provisional twig this morning. Life comes at you pretty fast, right? So as we start to go through these questions, all of these different things we need to be able to do from the perspective of we don't want to come up with a technological cul-de-sac. You have to look at it from a bigger picture perspective, right? And so what does that entail? That entails that we need to be able to say, hey, if we're going to have the ability to use block, file, object, we want to make sure that we don't have to have different paradigms for doing it locally versus doing it remotely. What does that mean? That means that it's not just so simply about I'm going to rely on PCIe as my solutions. Anybody who's ever worked on NVMe over fabrics knows that PCIe NVMe and NVMe over fabrics is not the same thing, right? There are things that you have to do when you start going remotely. And that's exactly what you're going to have to do when you start putting things onto a scale-up network or a scale-out network. These may be dedicated networks for specific purposes, but you're not going to be able to simply say, oh, the data is there, I'm going to access the data, I don't have to worry about X, Y, or Z. Right? Or for our Canadian friends, X, Y, and Z. So ultimately what we're trying to do here is we're trying to figure out ways of making sure that the data is correct, because that is the key part about the job about what storage is. The job of storage is, there's only one of them, and that is, give me back the correct bit I asked you to hold on for me at the right time. The magic word in that sentence is correct bit. Because all the systems that we do inside of storage, all the things that we do inside of our networks, is all designed to give us back that correct bit at the right time. If this happens to be inside of a really, really low margin of error, like a scale-up network where they're doing a lot of parallelism, or a scale-out network where the nodes have to communicate at a really low latency, right? If you're going to be doing that, you have to be damn sure that you're going to make sure that the bit is correct, right? However, what's the problem? Problem is, you don't really have a lot of time to do that. There was a paper that Meta did not too long ago where they were talking about the checkpointing time. It was not the function of the paper, it was part of the result. Given a certain number of GPUs, the amount of errors that goes on gets asymptotic. So they tended to checkpoint in this particular paper somewhere, I think, between 8 and 10 minutes. They quiesce every GPU for 8 to 10 minutes, at 8 to 10 minute time mark, so that they can checkpoint. Now, there's a whole bunch of things that are going on to try to make that a little bit better, right? Asynchronous checkpointing is what's a big issue right now, right? So there's a whole bunch of academic papers to talk about that. How do we get the direct access into from an accelerator into the data that maybe be tiered over time and so on and so forth. And all of these things are wicked cool, right? Like totally over my head on the math side. But at the same time, they are extremely cool because they are all trying to solve a very particular problem, which is how do I extend the length of the time that I can get these accelerators to work? So, what does this mean? It means that no one particular group can actually do this by themselves. No one particular person, no one particular company, no one particular group. Right? This is bigger than me. This is bigger than SNIA. This is bigger than a lot of different companies who are trying to solve these problems. That's one of the reasons why people have gotten so excited about this, is because of the fact that yes, somebody finally is going to stick their neck out and say, we can do this together. We can do this in an open fashion. We can have open conversations about this, and we can make sure that the work that we're doing is going to build upon the shoulders of giants. Now, inside of SNIA, we actually have a lot of different projects that have been done and started for different reasons, right? One of the data movers, right? We have a data mover, a software-based processor-agnostic data mover that was designed for virtualization. But let me start over that sentence again. A processor-agnostic memory data mover that also has data transformation capabilities. What do I have to do with the GPU processor? I need to transform the data so that it can use it. I have to move it from one memory buffer to another memory buffer. Does that not sound like what SDXI can do? And that's just one of the things that SNIA has been doing, right? SNIA has been doing all kinds of things with regards to security and management and data transportation. And we've got the work going on with other groups that are working with the specifications, just like OCP. We've got the transport work that we're currently doing with NVM Express and so on and so forth. So each of these different projects that SNIA already has involved, and I'll go over it in a second, already have some elements that are fantastic in and of themselves for their originally designed purposes, but have some pretty interesting and unique characteristics for the AI workloads as well, right? By doing that and building upon that, then we start coming up with a 1 + 1 = 3 solution. I take the one thing that I already have, I add it to another thing that I want to do, and I get a third thing that I can actually expand upon that. That provides a lot of holistic ability for us to be able to do this. So I talked about SDXI, that's the one at the very top. So what happens if I want to be a little bit creative? I want to start doing some of the data mutation, data transformation at the data location itself. And what if I want to do this on memory as well as I want to do this on data capacity? So in other words, I want to do processing in situ. I want to do processing near the data, near the memory, right? Why would I want to do that? Because I don't want to move the damn thing. What's the best I/O? The one I don't have to do. Think about this. Why would I want to move data if I don't have to? Well, I need to process the data, so why do I move the processor closer to the data itself? Why would I want to do that? Because I've got exabytes of the damn stuff. Right? If I can do the processing very close to exabytes of data, like a couple of years ago, Gary Greider came and talked about the kind of work that he's doing at Lano for this. Right? Petabytes of memory to do exabytes of data processing. Right? They do it in situ. There's no reason why this can't be done inside of an AI workload either. Right? The NVMe program model. Well, why do we want to do that? Well, because if I want to have a processor that communicates with non-volatile memory, wouldn't it be nice if I knew how to program that? Right? This was not designed for AI, but it could possibly be used or redefined for this. And the object drive work group, we just talked about this a second ago. I want to be able to handle the kind of data that is coming in. Some of it's unstructured, some of it's structured. A lot of it is unstructured. Right? So if I can do this, and I want to be able to do this in the same kind of metaphor locally as I want to do, or at least as close as possible, remotely, I want to be able to work on that as well. That was what we were talking about last night, and that's what we started talking about this morning, right? This is the old presentation. Flexible data placement. You want to know where to put it. You want to know where it needs to go. These are things that we've already started working on inside of SNIA. Security. Guess what that enables? 3 guesses. The first 2 don't count. But one of the things that I was in Taiwan at the OCP APAC Summit. The one thing that happened, you want to talk about, I think you were the one that was at the most popular thing, right? Power, thermals. Everybody was talking about power and thermals. How do I cool these suckers down, right? All kinds of things. You want to put liquid cooling on the drives. That's what we're talking about. And we're talking about different types of solutions that 5 years ago would have been science fiction. Right? And so as we start to go through this, what are the implications of this? Well, I'll tell you one of the implications of this is government regulations. Right? There are all kinds of government regulations going on for green, For energy, sustainability, we had hyperscalers talk about the sustainability yesterday. I think it was yesterday. And we had the energy efficiency stuff. Wayne Adams talked about it earlier in the week. And so when we start to talk about all these different regulations that are coming out, who's going to have a voice? Who's going to be able to talk about it? Who's going to be able to talk about it intelligently? And who do you need to do that? Well, you need the people who are going to have the ability to see the whole picture, right? Because government regulators do not have the whole picture, right? They don't care who you are. You're not going to find government regulators having a whole picture. So what about the stuff that we want to do? Well, we've already started talking about object over RDMA, right? And once we talk about doing a particular storage type over a transport type, the world opens up, right? There are different ways of solving these problems. And to say that, for example, we can predict what's going to happen in the next 5 years, make sure we go out for my time. I don't want to eat into Scott's. Okay, not too bad. So maybe it's going to be over Ultra Ethernet. Maybe RDMA means it's got InfiniBand. What about the scale-up transport? Maybe it's going to be over UA link, right? All of these different things are possibilities, right? Because we want to be able. We're expanding our definitions. You heard. Oh shoot! I'm blanking on his name, and he's going to kill me. We were talking about the memory pyramid, right? In the panel earlier, right? The memory pyramid moves. It is not a static thing. And as we start to create the expansion of memory tiers, HBM to regular DRAM to pooled memory using CXL and so on and so forth, that's going to change the nature of the game as well. Because now we have to work with CXL, now we have to work with PCIe, now we have to work with UA link and so on and so on and so on, right? That requires definitions, that requires ability to access it, that requires APIs and so on. What about the elephant in the room? Accelerators, right? And this says accelerator initiated I/O and bypass for a reason. There are more than just GPUs in the accelerator world. There are TPUs, there are GPUs, there are side-by-sides. There are individual projects going on in major companies and major organizations, as well as by startups. Addison had some great images of some people who are starting up on their hardware, right? Why would they not want to get involved in something that was going to be standardized? Well, now we have the ability to do so, right? Well, why do we want to do this? Because you can't just simply slap an NVMe device on a GPU link. It's not that easy, right? The durability of NVMe doesn't work if you're going to be doing, 5,000, drive writes in half an hour. We did a calculation internally. This is kind of amusing. I was talking to a GPU architect. I said, well, we can just put a PCIe lane there and just get an NVMe device there, and it can just be really slow memory. And I'm like, how often are you going to access this device exactly? Thousands and thousands of drive writes. And what happens during garbage collection, just out of curiosity? What's that? So part of this is going to be the education as well, right? How do you educate the people who are otherwise smart, but don't necessarily understand the nuances of what they're really asking for? So that's the other part of the equation. You can't just simply say, I want to do things better with an accelerator and expect it to just happen, because there's a lot of stuff that are implied in that many people may not necessarily recognize. So let's take a look back at this original example. We want to take the storage off of the front-end network, and we want to make it more efficient inside of the node. That means that we want to do the memory-to-memory buffer, communication and data movement. At the same time, we want to do it safely and securely. We want to reduce the amount of energy it takes to do so. We want to be able to have a good standardized way that the data can be structured on side of whether it be file or object, and be local or remote. We want to be able to tell the processors exactly where to read and write. So we want to have the placement of the data and so on and so on. But this breaks it down into a far more granular perspective. So now we're actually saying it's not just we're going to solve the problem through this gateway of a NIC or a DPU or an RNIC or something like that. We're not going to rely so heavily on the transport that it ultimately winds up that we're going to focus all of our attention on that one little bottleneck. No, we're going to distribute the work into the right place at the right time so that we can make micro-efficient adjustments. And that's where things become really kind of critical. Inside of SNIA, we have 2 different ways of doing this. We have what's called a community, and we've got a technical working group. For those of you who are new and not yet members of SNIA, I just want to give you an idea of how things are going to work. Storage.AI is a community, right? Think of it this way. Storage.AI is where people go to talk about what needs to get done, and the twigs are where people go to talk about how it gets done. So as you're part of a Storage.AI community, you can have the conversations about all the different pieces of those puzzle and how they fit together. Then when it gets to have the rubber meet the road, we talk inside of these different twigs. So we're going to talk inside of the security twig for security work, the memory data movement inside of SDXI, the object over RDMA or whatever the name is that they're coming to come up with. That's going to be done in that particular twig and so on and so forth. Then it comes back up to the community and say, hey, look, we're doing this. Would you like to be part of this, and where do you all fit in? It's this checks and balances that exist in this environment that makes it much more likely to succeed. This is not a top-down approach of this, you will do this. This is a, I think we should do this, and therefore let's work this out, and then come feedback up into the broader community. And we work with other organizations to do the same thing, right? It's a fractal approach. So ultimately what we want to do is we want to create standards, we want to create specifications, we want to create the tools, we want to do the tests for the performance, we want to give the opportunity for people to put these things together and plug fests and so on. We want to be able to educate people on what this all means. And we want to be able to establish positions that we can be friends of the court or friends of the government to identify what's going on. How do we do this? We define the terms. SNIA defines the storage terms. That's what we do. We've got a wonderful dictionary that's going to be used specifically to help guide us in making sure that we're all using the same language. Right? I've been playing around with some video generation as a hobby. And as I go through the top-down stuff, they use a lot of terms that we use on like seeding, for example, checkpointing. They use them in different ways. So having a lingua franca is going to be very important. But ultimately, the only way this is going to work is this is an open approach. Ultimately, at the end of the day, we have a choice. Right? We're at an inflection point. That inflection point is that we can either try to go all heads down and just, we're going to do everything just one way. Or we can say, we can think longer term. We can say there's going to be problems that we haven't even thought of yet, and we've got enough on our plate already. And we can accept the fact that there are enough smart people in different places that can work together. It can be a we situation, not an I situation. And that's what we're trying to accomplish with the Storage.AI. And this is going to be very important for SNIA's members, right? Anybody can participate in this. You belong to SNIA, you can participate. No extra charge, nothing to do, just show up, right? It's going to be really good for the implementers. Something that they can actually go to and they can refer to, and they can talk to their vendors, they can talk to the people who are going to be doing it and say, we want this. And it's going to be very good for the end users. Because they're going to have, and the regulators specifically, because they're going to have a place where they can actually go and say, I have a question, how do I find out the answer? Right? So by doing one thing, we can repurpose it over time. So if you haven't already, this QR code will take you to the community. So you can join the community right now if you wish. And so what we're going to be doing is next week, you may have seen me do a couple tests if you're already part of that community mailing list. We're going to start having the meetings very shortly. The SNIA board has identified that the Storage.AI community is in provisional status, which means that we're going to set up the charter and the scope of work and the identification with all the different technical work groups. And because of the fact that we've already been working on this and have the material, I anticipate that probably by mid-October, by the time we have the OCP summit next month, we will have an up and running community complete with charter and scope and work. If you want to participate in what that should be, I highly recommend that you anticipate. If you're not a SNIA member, that's not a problem. Come talk to me, come talk to Michael, come talk to Erin, especially Erin. And she will help you figure out the best membership level for you. Now, to that end, I want to thank you very much for attending. I know that many of you have come to the SDC to hear more about this particular project. I hope I was able to answer some of your questions. If I didn't answer all the questions that you want, please do come to the Birds of a Feather tonight. Right? because this is where I get to hear back from you, right? Where you can make fun of my hat and you can make fun of my name. Both things are fair game, okay? So if you want to talk about the things you want to do, Addison, you're going to be there? Or you have to leave? Addison. All right, fine. He won't be there. But we'll report back to Addison all the things that he needs to do for next year. All right, so I think, you sure? All right. I will entertain a question or two. Now, before I do, really quickly. When I say SNIA, God bless you. The thing is that SNIA is people, right? People who actually work really, really, really hard. And so the recognition ceremony is incredibly important because a lot of the stuff that we've done across the board for 25 years plus is because of people who actually do the work. And so please do stick around and give a profound thanks for those who are going to be recognized in a couple minutes. Okay, so any questions for me before we do? Stunned silence. I'm so clear. Okay. Well, thank you very much, everybody. I really do appreciate it.
All right. So as Jay mentioned, SNIA is volunteers. It's us doing our effort to put it together and help drive everything forward as a group of individuals. So what we want to talk about today is we do every January at our SNIA preview, we announce the previous year's winners, and then at SDC we provide them their actual awards. So on the page here, you can see that we've got quite a few folks that have been recognized this year. To kick it off, the first one we want to congratulate is Michael Horde. He was listed as our SNIA Volunteer of the Year for 2024. If you'd like to come up, we actually have some giveaways for you all. Wow. So he's being recognized as the individual picked as consistent contributions during the previous year and furthered work on existing programs. Excited about that. The next category you can see on the page is exceptional leadership, and so we have Anthony Constantine in the back. He needs to come on down and pick up your award. He's helped provide outstanding leadership to advance the cause of SNIA, and a lot of it has been focused on things like his work in SFF, which you'll also note is getting recognized. We also have an Unsung Hero Award. This is for the volunteer that everybody counts on, but nobody expects to be doing anything other than their best. And in the case of this one, we have two winners from 2024. We have Rick Cussall, I said that right? Of Broadcom, and Vera Kolavina of Coherent. Vera is not here, but Rick, please do come on up and grab your award as well. And then for those of you that are new to SNIA, we do have our New Contributor of the Year Award, which recognizes the person who comes in and just starts running with it. And Grigory, and I'm not even going to try to say his name correctly, I apologize, is the recipient of the award, and he is unfortunately not here today either. And then the last individual award is what we call the Excellence in Education. So SNIA puts a very large focus on educating, and we have some people that do a very good job of just putting it out there and driving that educational front. And in this particular case, we want to congratulate John Michael Hands, who is present, I think, somewhere in the room or was, and Igor, again, Chorjeskivis. Sorry, Igor, you're not here today, and I did not have to make fun of you in front of me. So, all right, so that is our last individual award. So I'd like to just highlight the folks that are here down front again. We also have groups of the year, and you can see here that the group of the year for 2024 was a cloud storage technology initiative at the time, which has been changed to a community, and the Cloud Twig. And then our last award is a significant group award, and that was the SFF Technical Work Group. And so those two groups have also been recognized, and we're very excited for the work that they've been able to do for us. So thank you, gentlemen. Awesome. All right, don't leave yet. Don't leave yet. Up next, we have a few other awards that we'd like to give out and highlight. There are Lifetime Achievement Awards. So our first, we'd like to recognize 2024's award recipient, Wayne Adams. Wayne is a longtime SNIA Chair, Treasurer, and Chair Emeritus. He's been active in SNIA for over 20 years. My first engagement with SNIA was when Wayne was Chair, so I really recognize and appreciate all he's done for us over that time period. He's active in the green storage work today, as well as the technical work there, and an active participant in a bunch of our board-level community or committees that we work on, like HR and budgeting and things like that. So he is just a stellar human being, and we're very excited to give him this lifetime achievement and hope he sticks around a little while longer. For 2025, our first honoree is Don Deal. Don has been actively involved with the SNIA in several different volunteer roles since 2000, serving as technical chair, technical council co-chair, SMI Twig chair, SM chair, treasurer, and SM lab chair. He participated in development of the original Bluefin specification, which later became SMIS, and contributed to SNIA in a very active role. He's also currently involved in the SNIA Swordfish specification. Unfortunately, Don could not be here with us today. And finally, our most camera-shy individual on the planet, S.W. Worth, is being honored as a key contributor in SNIA. He has been one of the #1 proponents for the educational aspects of SNIA and has driven so much for us in that front. He's also the CIFS conference and PlugFest supporter, and he helped with actually developing this conference. He's one of the originators of where this came from. And on his personal time, he continues to play a vital role in the development of the SDC, works on the SNW, has had major contributions on the SNW board and interest in that at the time of the effort, and he's been a member of the board of directors and technical council for over 10 years. So we'd just like to, again, give everybody a great round of applause. These guys have been putting in a lot of work.